with a theorem. Let A and B be vectors in R2. Then, the dot product of A and B is 0 if and only if A and B are perpendicular. So let's prove this. So we'll start with saying that the dot product is 0. So we'll say, suppose A dot B equals 0. Well, what is A dot B equal to? Remember our formula. So then the magnitude of A times the magnitude of B times cosine of theta is equal to 0. So therefore, we can divide by the magnitude of A and the magnitude of B. And this means that cosine of theta is equal to 0. And so now what are the values of theta such that cosine of theta can be 0? And we'll think about this in degrees just to keep things simple. So theta is equal to 90 degrees or 270 degrees. And so clearly, right, in a 90 degree space, we have our two vectors. And these are perpendicular. But 270 is just the, it's kind of a complement. 270 is just this angle. So in either case, if theta is 90 or 270, then A and B are perpendicular. And so this shows this first direction of the proof. Now we suppose the other direction. Suppose that A and B are perpendicular. And as we do in our diagram, right, this means that theta is equal to 90 degrees or 270 degrees, right? So therefore the magnitude of A times the magnitude of B times the cosine of theta is going to be the magnitude of A times the magnitude of B times 0, since cosine of either of these angles is 0. So this is 0. But of course this is equal to the dot product. So that shows this direction of the proof. Therefore, we can generalize the idea of two vectors being perpendicular to our n-dimensional space, or our Rn. So if we let A and B now be vectors in Rn, then if the dot product of those two vectors is equal to 0, we say that those vectors are orthogonal. And as with the last video, orthogonality is a concept that allows us to generalize. Because let's say we're in 7-dimensional space, it's hard to visualize vectors being perpendicular since, well, it's hard to visualize 7-dimensional space in the first place. But this definition gives us a very convenient mechanism to think about this idea of things being perpendicular, but applied in a new setting. This allows us to define a new concept called the orthogonal complement. So now instead of thinking of two vectors being orthogonal, we can think about two subspaces being orthogonal. So we say that if W is a subspace of Rn, then the orthogonal complement of W, noted with this kind of upside down T representing the perpendicular angles, and this is often pronounced W perp for short, because sometimes saying orthogonal complement takes a long time. So this is equal to a set of vectors x in Rn such that for all vectors in W, so we can say for all W in W, x dot W equals 0. So this is simply saying that the orthogonal complement is the set of vectors in Rn that are perpendicular to every vector in W. So if we think about 3-dimensional space and we have a plane, right, this subspace that spans a plane, the vectors that are going to be orthogonal to every vector in this plane are going to be the normal vectors to this plane. So the orthogonal complement to a plane or a 2-dimensional subspace is going to be a line, or a vector space spanning a line, or a 1-dimensional subspace. And so there's an interesting thing that we see, and I won't prove it here, but the dimensionality of a subspace and its orthogonal complement add up to the dimensionality of whatever total space there is. So for example, in our three-dimensional space, we had our subspace that's a plane that spans 2 dimensions, and then the orthogonal complement spans a line, which is 1 dimension, and 1 plus 2 is 3, and we were looking in 3-dimensional space in the first place. I want to end this video with a theorem, specifically that if W is a subspace, then the orthogonal complement of W is also going to be a subspace. So there are 3 things that we need in order to show that a set of vectors is a subspace. The first is we need to show that it contains the 0 vector. The second is that it's closed under addition. And the third is that it's closed under scalar multiplication. So first, we want to show that the 0 vector is in the orthogonal complement of W. So we can suppose that W is just some arbitrary vector in our vector space W. Then the 0 vector dot W is, well, it's 0 times W1 plus 0 times W2 plus all the way up to 0 times Wn. And of course, this is just going to be adding up zeros, so this is equal to 0, which means that the 0 vector dot W, any vector in W, is going to equal 0. So 0 is orthogonal to every vector in W. In fact, the 0 vector is orthogonal to every vector. This shows this step of the proof. The second step is to show that W perp is closed under addition. So we say that if 2 vectors, x and y, are in the orthogonal complement of W, then their sum, x plus y, must also be in this orthogonal complement. So we'll do a similar thing. We will suppose that x dot W is equal to y dot W, which is equal to 0, for all vectors in our original vector space. Therefore, we want to ask, how about x plus y? What is the dot product of x plus y and W? But in the previous video, I showed that there's kind of a distributed property. So this is equal to x dot W plus y dot W. But remember, these are both equal to 0. So this is equal to 0 plus 0, which is equal to 0. So we have shown step 2 of this proof. Finally, we want to show that our vector space, our orthogonal complement, to show it's a vector space, is closed under scalar multiplication. So this means that if we have a vector x in our orthogonal complement, and we have some scalar c, I'm using this f here to denote that it's an element of a field, then c times x is in the orthogonal complement as well. So we suppose that x dot W is equal to 0 for all of W in the original vector space. Then Cx dot W, remember, is equal to C times x dot W. This is equal to C times 0, which is simply equal to 0. Therefore, we have shown all the requirements that the orthogonal complement is a vector space if it is the orthogonal complement of a vector space, which is what we wanted to show.